Hello and welcome. I apologize for the extended intro there. As soon as I went live, or as soon as it was about to be time for me to go live, I was like, hey, I should go do all these things I just put off doing until the last minute. Hey, what's up, Mrs. Tribune? Welcome. Hope you're having a good night. um, yeah, anyway, so to get into it here, I got some new stuff to bring forward, some new interferometry experiments that we're gonna cover and go over. Um, This is 1942 Dufour and Prunier, and these guys, what they did is they did additional experiments supplementing the Sagnac effect, right? So in 1913, when Sagnac came around and showed that there was an interference pattern in a rotating interferometer in uniform motion, excuse me, I apologize. Special relativity said, well, it's a rotating reference frame, so it's non-inertial, so relativistic effects don't apply. Yada yada, we're all good here. And then, excuse me, one second. Yeah, so relativity was like, hey, we're all good here on the Sagnac effect, rotating device. We can't explain it. So in 1915, the general theory was starting to pop off. In 1918, a man named Paul Lavue came up with a metric tensor to explain the Sagnac effect within the general theory, and then, of course, being linked with the equivalence principle. Um, the Sagnac effect was co-opted into a relativistic effect. So what they did with their special metric tensor to describe angular momentum on the small scale was they said that the rotating device generates a gravitational field equivalent to generating enough length contraction and time dilation to facilitate the fringe shift pattern. So that's how they got away with it, because in general relativity, energy and all that is uh, all that goes into the gravitational field, right? It's all equivalent. So the energy of the rotating device, yada yada, right? So they got the relativistic answer. One second. Now the relativistic answer provided is contingent on one thing, and that is that the Sagnac effect is actually due to rotation, right? So if it's not due to rotation, then all this fancy math that they came up with and all these gravitational fields and equivalences and principles and whatnot is all just made up, right? So we're going to get into an experiment done in 1942 that should have been done, immediately after the Sagnac effect, right? But for reasons unbeknownst to us, or unbeknownst, or whatever that word is to us, is we'll never know, right? So anyway, these guys came along, Dufour and Prunier, in 1942, and decided to do subsequent Sagnac experiments, which I'm gonna read through and give a little commentary on it, that sort of thing. We'll look at their devices. Oh, why isn't all this highlighted? Hold on one second. Where's my highlighted one? There we go. All right. So we're gonna read through and give a little commentary, talk about what they did, show some diagrams, get everyone familiar with this, and then and then at the end of this, if it doesn't go too long here, this is 15 pages. So if this doesn't run on too long, we'll get into a review of it by Robert Bennett of this experiment and what it means and the implications of it, right? Because for every experiment, there's interpretations to what's being implied there, right? So we don't necessarily have to go with the relativistic answer. We're going to find out that that's not a viable solution here anyway. So moving on a fringe movement registered on a platform in uniform motion, 1942, by Dufour and Prunier. In a series of experiments described herein, we used an optical circuit. We used an optical circuit entirely fixed to the rotating platform, as Sagnac previously did. Under these conditions, we found that the movement of the fringes observed are similar within 6%, whether the light source and photographic receiver be dragged in the rotation of the platform as the experiments in Sagnac, or if they remain fixed to the laboratory. So this fixed to the laboratory thing right here is going to be very significant moving forward, differentiating the Sagnac effect, and then later supplemented by Ruyang Wang. But we're not going to get into the Wang stuff for now. But this is a huge piece of the puzzle, so to speak, right? In terms of interferometry and how to interpret these effects, and how the Sagnac effect was co-opted, and how you could show that it's it's not the effect isn't due to rotation, right? So the second series of experiments described here was aimed to explore the fringe displacements due to rotation in entirely new characterized or conditions characterized by the fact that the optical circuit of the two superimposed interfering beams is composed of two parts in a series, one which remains fixed in relation to the laboratory, while the other is attached to the rotating platform. So we're going to see some interesting configurations here that these guys came up with to test, um, what's going on with the behavior of light in relation to a moving or stationary observer. Moving fringes obtained under these new conditions uh, were one that allows for the classical theory. So, the classical theory being an ether theory, where the optical circuits are where the optical circuit is fully fixed to the rotating disk, as in Sagnac's experiments. The observer does not have the means to make the choice of interpretations of the placement of the fringe data obtained by theory of the classical theorist and of the relativist. So, one second. All right, sorry about that. Okay, so let's see. Yeah, so the theory of, hey, in this reference frame, blah blah blah, right? Or hypothetically, the light would be determined from this, point of view or whatever, right? So this is getting into ways to differentiate the the mathematical covariance, which is an assumption yet to be proved. Um, Robert Bennett said that's a good way to quote, or a good way to put it. So it's a mathematical assumption that's yet to be proven, that you're just working with for a working hypothesis, so to speak. So anyway, these experiments will start to differentiate like the cause and effect, right? So that's what they're getting at here. So let's see. The relativist theoretician cannot agree with the classical theorist, nor can the results observed, assuming one had done until now, that the center, where the observer must presume to be positioned to calculate the experience, can arbitrarily be chosen on the rotating platform. This center must be collinear with the center of rotation of the platform. And we'll get into what this means shortly, but to give a short synopsis of it, is basically in relativity theory, if there's a rotating disk, like a merry-go-round, for example, you should be able to derive the motion between two observers from any point on that merry-go-round. There should be no preferred uh, position in which you have to derive motion, right? So what they find here is that the relativity only gives an agreement with a when it's basically in the favored position of being stationary and not rotating, um, on the basically being in the center of the rotating device, is the only way that relativity can provide an answer here. So we'll get into all that. So one, experiments in the optical circuit is entirely supported on a rotating platform. So this is a closed beam on a rotating platform, right? So like a lazy Susan set up with a triangle configuration, and a beam of light just reflects in a triangle. Very straightforward. So preliminary experiments. So that we could familiarize ourselves with the experimental difficulties, we first of all had to repeat the Sagnac, or the experience of Sagnac. in which of all the optical apparatus is, as we know, moving with the disk in uniform rotation. So this is a really good point because you'll see in later Michelson-Morley type experiments, they'll say, "Oh, the because of better technology and whatnot, the experiments, the fringe shift pattern is trending towards zero, meaning that they're showing a speed of light being the same." But they don't reproduce the Michelson-Morley experiment analogously to how it was originally done, and then go from there. They go with these modified configurations that lead to a result that doesn't allow for the fringe shift pattern to be shown. And Dayton Miller did, hundreds of thousands, if not millions of measurements, controlled measurements in a lab in case physics school for years, where he was figuring out all this and how to, so spoof the fringes, so to speak, to get it to give no result, to give no fringe, basically. And you'll find that these, modern Michelson-Morley experiments, all air quotes, that they're not even they don't do this process where they're like, hey, we're gonna do what Michelson did, see what that gets, then we're gonna do this new thing, see what we get, compare and contrast. No. They do it in such a, and they don't, anyway. So we'll continue on. Let's see, where were we at? We used to that end the same mirrors which had been used by Sagnac in his experiment, but the platform that we used was twice as large as his, and it had here 1 meter in diameter and could turn at a measurable speed, not exceeding, however, 5 rotations a second in the direction, or in one direction and then in another around its axis of revolution, standing upright. This axis was defined by a line through the final points of the rigid tree supporting the disc, points swiveling in cups of grease pans carried by a solid frame sealed with the wall of the laboratory. The assembly removed any play during rotation of the apparatus and allowed, however, the easy maintenance of its movement without harmful vibration. The torque was supplied by a small dynamo set at the same wall. Transmission of this couple was obtained through a belt acting on a pulley connected with a tree to the platform, or with the tree of the platform. This material arrangement has remained the same for all experiments that will be discussed here. Figure 1 gives the layout of the optical apparatus straddling the entire disc and used in these preliminary tests. It is close to identical to that of Sagnac and does nothing original. So they took real careful. They even used some of Sagnac's original equipment that was available, and really strive to reproduce the actual effects before even moving forward. Right. So very cool. The separator used by Sagnac could not be found and has been replaced by the beam splitter. Separating the receiver are not silver plated, and the receiving rays under a rather large incidence. At the end of the light source, through the S collimator, comprised of the entire lens L and diaphragm O in its housing, and then upon reflection, auxiliary M has given two beams interfering, which splits in C at the center of the disc and goes in opposite directions. One path C, M, M prime, M double prime, M triple prime, and then back to C. And the other path goes to C, M triple prime, M double prime, M prime, and then M, and then back to C. So this is what this is a topographical view of the device and the mirrors. So the beam sets out, gets reflected and all that. Comes back in after it hits the recombiner or whatever, and then there's a photographic plate housed in here. That's where the fringe shift goes, or that's where the fringe shift goes. Like, it lives there. It goes home after a hard day of work of traveling from here to here, or whatever. Anyway, Yeah. So anyway, this device also rotates, and then it rotates in the opposite direction, and they get their French shift readings and do a compare and contrast. After the meeting out of C, these beams are returned by an auxiliary mirror N to the lens O prime, which makes it possible to obtain, after the last auxiliary reflection out of P, the real fringes on the photographic plate go to P. So right around in here. In consequence, oops, let's change this. Not that it really matters. Let's see. In consequence of the low intensity available on the photographic plate, we almost always have to operate in white light the AGFA panchromatic plates of great, or with chromatic panchromatic plates of great sensitivity. It results from that the measurements and the displacements of the fringes made on all our photos are obviously affected, but not or affected by not very important errors and variables in connection with the spectral composition of light used in the selective sensitivity of the emulsion, emul, uh, emulation. I don't know. Emulsion of the various series of plates in the various wavelengths. So, in spite of this imperfection, the significance of this result obtained remains whole here, the qualitative point of view. Moreover, even from the qualitative point of view, the extreme variation of the numerical results, even one series of recordings never exceeded 13 per 100 of the median value. The order of magnitude of this thus remains valid. Valid and significant. So I honestly don't understand. There's not many people here yet. Always give so much information in one show. It's astounding. Yeah, thank you. It's yeah, it's a lot to take in. It's even new. Like even I like like I'm finding out new stuff every time I read this. You know what I'm saying? So it's all good. So yeah, what homie's saying here is that despite the change in the wavelength of light, it didn't really seem to affect the readings very much, and everything was still very similar to Sagnac's to the measurements that Sagnac got. So the experiments made with the device one were or figure one were precisely used by us to calibrate the indication of the photographic recordings according to the values of the Sagnac effect in white light for the particular plates which were used. For each direction of rotation, the exposure time was of a fraction of a second. The determination of the number of constant revolutions during the exposure was obtained by the measurement of the number of revolutions of the platform during 2 minutes with a stopwatch. One recorded the plate fringes obtained initially for the one direction of rotation, then for the other direction. So it does its clockwise and counterclockwise rotation. The magnetic remote activation for the two small shutters made it possible to protect successfully each half of the plate against the action from the white light. One thus obtained the two system of fringes corresponding to separate directions of rotation, one from the separate directions of rotation, one from the other by the line, facilitating their comparison. The measurement of the distances between interference fringes and the shift of the fringes was uh, taken by pointing a dividing machine. The machine was drawing a precise equidistant lines. Let's see, kind of spaced out a little bit there while I was reading, so I'm gonna reread this real quick. So the minute, what were they going over? So the calibration for how they did the recordings or whatever. The magnetic remote activation was the small shutters made it's possible to protect this. Okay, two fringes corresponding different directions, facilitating. Okay, the measurement of these distances and fringes was taken by per point by a dividing machine. Oh, okay. So they use like a pre-calibrated, basically like a protractor kind of thing, where it already has its equidistant line set up so you can get your accurate readings, right? So the average of 9 recordings on the ordinary Sagnac effect gave us this value effect of 0.081 at the distance between the interference fringes for the angular velocity of 1 turn per second for the two directions of rotation, the light source being the filament of a fairly good equidistant or equidistant incandescent lamp. The order of magnitude thus observed for the ordinary Sagnac effect appears well in agreement with one that could envision by taking account of the position of the approximate center of gravity in the spectrum and of the action of light on the panchromatic plates used. Besides this, center of gravity defines the effective wavelength for the calculation of the phenomenon. In the formula of Sagnac, which gives a fraction of the distance between interference fringes of the value delta of the total fringes for the two directions. So we have delta equals 16 times pi times n times a over n times a over c times lambda. N is the number of revolutions per second of the platform. A is the value of the area of the closed path that light has to travel. So basically go down here. So just all this total distance added up, that's your area. And let's see. So c is the speed of light, and lambda is the wavelength used. So when they were talking about the where was it? That doesn't matter. The white light spectrum that they had to use, that's what they're referring to for the calculations. So in our experiment, the surface area was approximately 2,842 centimeters squared. The experimental results obtained thus have given us license to deduce that the wavelength lambda has a value of approximately 0.57 when the sources consisted in an average incandescent filament fairly pushed 0.54 if it is more brilliant 0.45 if it is white light crossed a Scott screen out of bluegrass, almost said bluegrass, out of bluegrass, letting pass only the region of the spectrum from 0.5 to 0.36 so not a big change there when using different materials. One second. So the two experiments made with the light source remaining fixed to the laboratory. So the first question that we considered to determine if the movement of the source, that if it was the movement of the light, or the movement of the source of light that creates the phenomenon, right? So we then constructed an apparatus shown in diagram 2 or figure 2 here. The characteristics of this assembly are to use the light of a fixed source of the laboratory and send it through an optical path course that's fixed to a rotating platform. In the shapes and flashes repeating itself, to which the turn of the disc passes on the same position. So what they got here is, instead of having the source of the light on the device as it's rotating, right? They're going to have the source shoot the beam in here, and it's going to hit that, reflect in, and all that, and that they're going to get their readings that way. So they're going to try and differentiate, like, is it does the movement of the source of the light have anything to do with the fringes, right? So this is a really cool experiment that they did here. So for this purpose, the light resulting from the source S will traverse the lens L and to the diaphragm T and the microscope objective S. All of these bodies maintained fixed to the laboratory. Another microscope objective R, identical to the first, is fixed in the revolving platform and projects the image to the diaphragm O thanks to the auxiliary mirror Q. And the image on the diaphragm T is equal with O when the platform has precisely positioned when the platform has precisely the position indicated on on the figure. The S square line is directed so that its extension passes through the center of C at its rotation. So this objectives R and S work under good conditions at the same time of flash. So he's just talking about the logistics of getting a reading of a rotating device while you're on the stationary perspective instead of having it on the device, right? And how it's just when you have it aligned in such a way as it's making its rotation, when it hits this precise position, they're able to get their readings. Okay. All right. If V is the linear velocity of the objective R and G is its magnification, the linear velocity of the image diaphragm T on the diaphragm O will have a value approaching VG of the duration tau of of the flash, and thus it will be to the order of tau equals VG over D if D is the diameter. Here, the common diaphragm O and T are here common diaphragms O and T. In our experiments, C times R equals 45 centimeters, G equals 10, D equals 1.5 millimeters, which gives for an angular velocity of 4 turns per second. So tau equals 1.3 times 10 to the minus 5 seconds approximately. So a really short window of time, right? So what would that be, like 13? Hold on, I had it in my notes. I think it's 13 nanoseconds or 13 microseconds or something like that. Really small amount of time, right? Fractions of a second. So let's see. Thus, even at this speed, each flash of the duration T of the useful beam of light, it is quite high at the runtime of light along with the circuit optics. This one has indeed approximately 3 meters length. It is consequently traversed by the light in 10 to the minus 8 seconds. Each beam thus makes at least 1,300 times its turn of the optical circuit during a flash. Fringes thus have a large time to be formed on the photographic plate. However, to obtain one sufficient photographic impression under these experimental conditions, the installations will have to be longer than the installations will have to be longer than in the case of the trained source. It has been necessary to wait approximately 5 minutes here for each direction of rotation by using the same source of wavelength of light. So they say there that, because of, how quickly it's rotating and all that, they just have to let it rotate a little longer so that the image burns in so that they can get a good reading. All right. Very cool. The recordings, which are carried out, thus show a net shift of fringes completely comparable with that provided by the traditional assembly of Sagnac. The average of the results of the measurements are made in a series of 9 photographs, led to the values of 0.088 distance between the interference fringes for the shifts of the fringes corresponding to the 2 directions of rotation and 1 angular of the platform of a 1 turn per second velocity. The variations of the individual results reach to more than about 15 over 100 of this average. It is seen that to 5 to 6 per 100 close, the average shift observed is the same value here than that obtained with an ordinary assembly of Sagnac. So, with a stationary light source emitting the light, the rotational effect doesn't seem to have anything to do with it. The effects still persist. Or I'm sorry, the actually no, a more accurate way to put that would be the movement of the observer doesn't seem to have any effect on the displacement of light, and it's still producing an effect as if the observer is rotating. Okay. Specimens uh, specimens of recordings reproduced here in Figure 3 represent increased four times to two of the original photographs. The direction of rotation relative, respectively, to the upper parts and of the lower parts of the same photograph are opposite. Stereotype 57, number of revolutions, 4.13 turns per second. Watch the Sagnac effect obtained with the traditional device or the source pulled by the disc in photograph 45. Number of revolutions, 4.39 turns per second, is a recording obtained here under current conditions, i.e., where the source is fixed in the laboratory. The ones where the shift of the fringes are appreciable, even with the one sees that the shift of fringes is appreciable, even in these two tests. Okay, so they got the same exact readings, obviously within a margin of error, but they more or less reproduce the Sagnac effect, and they showed so far that the effect persists regardless of the movement of the source. Three, experiments made by using the source and photographic recorder remaining fixed to the laboratory. One could ask whether the one could one could ask whether the interferential interferential phenomenon remains the same for one observer fixed in rotation and for one observer that's maintained fixed in the laboratory frame. To carry this study out, the device represented schematically in Figure 2 underwent the following modifications. The mirror P was removed, the objective lenses L prime and the eyepiece O prime, as well as the photographic chamber P, were removed from the platform and fixed to a support motionless with a seal of the wall to the laboratory in the manner as to be placed in a straight line that places suitable one path of the reflected light by the mirror in at the time of the flash. This arrangement, the source of light and the observer operating the photography of the fringes when the lenses in the photographic chamber are both fixed in the laboratory. I'm sorry. Yeah. Yeah. In this arrangement, the source of light and the observer operating the photography of the fringes with the with the lenses in the photographic chamber are both fixed in the laboratory. Right. So, but throughout Flash, very short, though non-null, the platform turned a small angle, and the fringes obtained on the photographic plate underwent a light modification because the lens and the plate are motionless while the interferometer is turning. To eliminate from this measurement any possible cause of error, we used a known change of the sign of the Sagnac effect when one swivels a small angle S around a vertical axis separating ISR on both sides of its average position, providing a central fringe extended on the interferential field. On the photographs obtained when the angle positive, let's see, On the angle positive, the shift of the fringes due to the rotation of the interferometer during the flash will be added, for example, with the Sagnac effect. On the contrary, for the photographs obtained when the angle, I can't remember what that is, epsilon, I think, is negative, the shift in the fringe due to the rotation will be cut off from the Sagnac effect. By taking the average of these two series of recordings, the value of the Sagnac effect will be obtained corresponding to one negligible duration of flash. Naturally, the precision of the results suffer a little in this additional difficulty. In spite of this, the values found remain similar to the preceding ones. Thus, the average of the shifts and the fringes were given by 10 stereotypes in each of these series of the two directions of rotation and the angular velocity. Let's see. Thus, the average of the shift of fringes given by 10 stereotypes in each series for the two directions of rotation and the angular velocity of 1 turn per second is equal to 0.098 distance between the interference fringes for a certain sign of epsilon and to 0.084 distance. Distance between the interference fringes for the other sign of epsilon. The average of these two values is 0.019 distance between interference fringes, differing only 3 to 4 over 100, the number obtained previously if the source of light were fixed in the laboratory. So again, they were getting similar results with their new configuration, which we're going to see here as we scroll down. Let's give it 1 second. Let's see. So what they were doing here is they were inducing an artificial fringe that would be canceled out by the effect that they were having an issue with or whatever, right? So that they could kind of zero that out. So they took another known effect produced by having a certain angle tilted to one of the mirrors, and that would cancel out during rotation, or as the device rotates when it gets its readings. So let's see here. Where were we at? Okay. Photographs 98 and 86, angular velocity of approximately 3.7 turns per second, given in figure 4, represent increased 4 times 2 of the original photographs obtained under these conditions, and for which the direction of rotation of the platform is the same, and one which relates to the higher areas for the recordings. For the lower parts of these photographs, the direction of rotation is opposite to the previous. The angle epsilon was of a certain sign for photograph 86 and of the sign opposite for photograph 98. One realizes at first sight that the average of the absolute values shifts of fringes in stereotypes 86 and 98 is of the same order of magnitude of the fringes as detected by stereotype 45 on figure 3. This result is related to the fact that the platform turns of a very small angle throughout the flash. So, experiments in which the optical circuit includes a fixed part to the laboratory and a pulled part by the platform rotation. So preliminary test. Figure 5 gives the perspective of the diagram of the first device which was tested. So they got the mirror splitters here, and they're angled up, and they hit another configuration that's positioned above this and angled slight, and then that's it redirects it towards the wall. So when they have a rotating device, stationary device above this, stationary recorder or stationary photograph, blah blah blah, all on the lab wall here at S, right? And then we got our rotating device here. So this is a really cool setup here. So the light resulting from the source S crosses the collimator L prime not drawn as it comes to provide by action of the separating beam splitter G to the interfering beams with distinct paths. One path G F E D R and the other path G, F prime, E prime, D prime, R, the fringes are observed in the lenses L. All right, so one more time. Oh, okay. So I'm sorry. I had it backwards. So source here hits the stationary stuff here, rotating the other half of the device rotating. It's not connected to the stationary top here. Anyway, the rotating under half is rotating, hits here, reflects out, and you observe it here from a stationary point of view, not connected to this rotating device or the rotating half, so to speak. All right. So the source. Let's see, read that. One path. Okay, the source of the collimator. I think I just is that the part I just read. The source S and the collimator L prime and the mirrors G, F, and F prime are fixed in the lab. The other sources of the mirrors, as well as L and the photographic plate, are carried by the platform and turn with it. Consequently, the only portions ED, R, and E prime, EDR, or sorry, E prime, D prime, and R of the light path is fixed on the direction or on the disk of rotation. Lastly, the provision of the mirrors is supposed perfectly symmetrical compared to the plane of GCR, in which the line C and G is collinear with the axis of rotation X and X prime of the disk. The experiment carried out in accordance with this assembly could not lead to the effective recordings because it was necessary to operate in a monochromatic light of which the intensity would be insufficient to impress here on the plate without excessive duration or durations of installations, and especially because the small ground vibrations scrambled the system of fringes, which would have removed any significance in the discussion. So not able to get any results out of this one, out of this configuration here. So I thought this one was the one where they were taking the readings from a stationary perspective as well, but this configuration, the readings would have been fixed to the rotating device as well. So it would have just been the source and rotating. So in the other, wait a minute, the other one was the same. Now I'm getting them backwards. I think I'm getting him. I'm getting him confused with this one or with the next one that they did. So the preceding disadvantage resulted owing to the fact of the two interference beams followed the distant path. They disappeared when they obliged the two beams of the following or to follow the same course in opposite direction. Figure 6 gives a perspective of the diagram of the apparatus constructed, which was useful to us. So we got a similar configuration to what we had above with a rotating device stationary above, and then obviously fixed to the wall being stationary. So the collimator L prime and the lens L is not drawn. The beam splitter S separating and receiving where O or where the observer 0 is supposed to be. The plane mirrors K, J, D, E, and F are all fixed to the platform and turn with it. The beam splitter planes S is about the equal distance to the mirrors J or F and J. In addition, the radial length of C and F and C and J are equal to them. Mirrors G, H, and I remain fixed to the laboratory. For all the mirrors other than F, J, F, G, I, and J, the plane of incidence are horizontal and parallel to the platform. And here they kind of have a poorly lit picture of what they had going on here. So the rotating apparatus underneath here, and then they had a fixed apparatus above where they were, like basically an inverted tabletop, where they had their configuration set up where the beams would reflect up and then reflect out to the wall as the device would rotate underneath it. It would when it would align properly, everything would connect out and they would get their readings. or well, I said that backwards. So the the source was mounted here, was light was reflecting in. They were getting their readings on the device in this configuration. Only the planes of incident of the mirror F, J, I, and G are vertical and contain the axis of rotation X, C, and X prime. The last mirrors are tilted at a 45-degree angle on the vertical mirror of F being parallel with the G mirror, and then the mirror J parallel with mirror I at the time of the flash when the light provided by the source not drawn fixed to the laboratory and consisting of a carbon arc. Lasting lengths FG and IJ are parallel to the axis of rotation, equal between them and of a value of 10 centimeters. One of the interfering beams of the path SK and J on the disk, then JIHGF, path remaining fixed in the laboratory, and returns by the path FDES carried out by the disk. The other beams goes in opposite directions of the path. The fringes are recorded on the photographic plate, were related to the platform delta, and are located on the focal plane of the lens in lens L. Figure 7 is a photograph of the experimental device such as it was used. The source of light is not visible here, being to the left out of the field. The turning disc of the vertical axis is surmounted by a second platform fixed to a frame sealed with the wall of the laboratory, and which carries the mirrors to the upper platform. Those are actually 5 and not 3, like in figure 6 indicated. Indeed, it is obviously impossible to place the plane mirror H fixed in the axis of rotation of the revolving platform. Thus, this single mirror H was replaced, in fact, by 3 plane mirrors, which one sees in figure 7, and which makes it possible for the interfering beam to circumvent the 3 of the mobile platform, not to be intercepted by it. But as the higher course of the beams is fixed, the laboratory and the azimuths of the planes of incidence in the mirror G and I remain unchanged. It was more convenient to use the reasoning what what it is we all will do, or what it is we will what it is and what it is we oh man and it is what we will do. Jeez, sorry, I had trouble with that one. And the plane mirror is fictitious. Plane mirror is fictitious figure in figure fictitious 8. The plane mirror fictitious H in figure 6 to replace these 3 mirrors. The reality of the reality of figure 7, which are equivalent to it in the experiment. Okay, yeah, so gotcha. One can wonder, however, if it is reasonable to hope to obtain fringes usable with such an interferometer that is already rather complicated, and of which 2 parts are moving relative to one another. It is thus necessary, even required, to manage to maintain sufficiently or to obtain sufficiently definite fringes from handing unchanged throughout this flash in spite of the movement of the revolution of the platforms. These 2 conditions could be satisfied in constituting the upper floor of the device by 1 odd number of plane mirrors and by 1 equipping the apparatus with an additional plane mirror D. Below are the reasons for having such provisions. 1. For a short length of time, but non-null, the flash during the rotation of the platform in the direction of the incidental beam of light does not change hardly, but the mirrors F and J fixed on the turning platform move a little compared to the beams which they respectively receive from the upper floor. However, the fringes used are ad infinitum localized, and each one of them is provided by a whole group of rays. So these fringes do not undergo modifications. It is necessary that the whole of the ray of each interfering beam remains in a relative position compared to the mirrors that they have met. The conditions, which particularly relates to the mirrors at a 45-degree angle, F and J, fixed on the rotating plate or revolving plate. However, if one observes in J the luminous spot provided by the beam going in the direction F to G towards J, and the luminous spot of F provided by the beam going in the contrary direction of J with I towards F, one notes that the luminous spots of the little or that the luminous spots move in little consequence of the rotation of the movable platform delta, and in opposite direction when the fictitious mirror H is replaced by a number of plane mirrors, two, for example, to transmit the light of G at I and I to G. In such conditions, one can obtain fringes, mirror D being then supposed to be non-existent. But these fringes narrow and widen according to the direction of rotation, even when very slowly. These modifications of the fringes result owing to the fact that the large group of light rays does not meet each other in the mirror F and J, always in the same relative position during their platform rotation. But if an optical course of G with I is carried out, and at the time of the upper floor by the odd number of plane mirrors in the direction of the change of this displacement out of F and J from one beam is so throughout the flash the areas of the arrival at beam X on the mirrors of F and J accompany the latter during the rotation. The fringes which obtained then mirror D supposed position back, one will further one will see why further one will see further why remain unchanged during the last fringes of its revolution is negligible as shows in photograph 142, increased approximation approximately 4 times of figure G. Reason number 2, if the mirror in D did not exist, the number of mirrors located on the light path would be odd, here equal to 9, and it is known that, and for this type of interferometer, the number of mirrors must be even so that the corresponding rays are found on the beam splitter. The the presence of this mirror thus is necessary so that the rays separate with various points of the beam splitter. Beam splitter do not provide their return on this beam splitter. Two beams split turned over, one compared to one another. Number 3, but the existence of the additional mirror D is made compulsory for another reason. Its role is that it is to compensate for the modification of the points of impact of the rays on mirror F and J at a 45-degree angle. This modification being due to the displacement of the mirrors throughout the path of light on a mobile platform in the upper floor carried by another fixed platform in the laboratory. So figure 8 represents the purpose of the revolving platform seen in plane. Points A and B are marked respectively, starting at the arrival points of the interfering here at the beams. Here are the beams shown with only one ray, the motionless platform being shown, and the adjustments being such that the rays on one turn coming from an incident ray come to be cut on a separating beam splitter. Under these conditions, the ray circulating under the direction starting from M arrives on mirror F, goes up from the upper floor, goes out again from B and on mirror J, which returns to M, and just going over the directions of the mirror and the paths and all that and why they had to do it. So basically to compensate for the effects of the way that they were having the device orientated so that it gets 45-degree deflection so that it goes upward so that it hits the stationary reflections. He's just going in detail about the about all that. So sorry, it's kind of a little boring here on the detail side of it. So I'm just going to kind of skim ahead here. Let's see. It is worth remarking that the returning rays maintain the same direction provided that they follow the path traced on the platform delta, whether this platform is rotating or not. From this, the parallelism of the condition A prime equals B prime, one deduces that the rays returning from B prime K1 to VI prime and A prime to DEM M prime or M double prime cut the separating beam splitter at the same point so that M prime and M double prime are collinear. It it is also a result from this corresponding fringe that an ad infinitum remains on the disk delta at the same rotation ML, or at the same direction of M and L as the platform was motionless. But the question arises at once whether the aspect of the fringes remained unchanged. The two assumptions here are considered. The first assumption, the speed of light on the platform remains at a constant equal to c, whether the platform is motionless or moving. The frequency of light preserving on the disk, one constant value, one deduces in this case that the light of the parallelism noted above is the returning rays arriving of M prime and M double prime are opposite one another under the same relative conditions of the phase of the platform it did not turn, under the same relative conditions of the phase as if the platform did not turn. The results from this that fringes recorded on the photographic plate are modified by neither aspect nor positioned by the act of rotation on the platform delta. The second assumption, the propagation of the velocity of light on the revolving platform depends on the direction in which it travels. Oh, interesting. In which case, in this case, the travel of the rays traced on the platform does not change immediately, but in a new factor, but a new factor intervenes. It is a delay brought between the light rays and the inequality of the speed of light propagation. The delay, which modifies the order of the interference to the fringes laid out to the remaining direction, however, constant to ml. So this result would effectively is an equivalent displacement of the fringes of the photographic plate. But ultimately, it is seen that these two assumptions, changing the position of the points of return of A prime and B prime of the rays resulting of the rotation, may not by itself cause the changes of appearance or position of the fringes of the photographic plate fixed on the mobile platform. In the more general case where the two interfering rays would leave one after the other points A and B, the reasoning of reasoning similar to preceding shows that M and M prime would not be collinear anymore, but the conclusion given above would always be valid. Lastly, it is advisable to point out the possible existence of the aberration effect along the vertical paths F and G and J and I in figure 6, but the linear velocity of the actuated mirrors F and J not exceeding in our experiments 9 meters a second. The obliqueness which would affect the rays FG and JI reaches 6/1000th of an arc second, and wow, 6/1000th of an arc second. That's crazy small. So 1 arc second would be 1/3600th of a degree, and then he's saying that just one of those, this is 1/6000th of an arc second. In consideration here is completely negligible. Yeah, so not even perceptible. I don't even know how you would. That's crazy. So in short, with the device thus implemented, any modification in the appearance of the position of the fringes when the angular velocity of the platform is in one direction or the other is extremely small. It follows that the experiment made with the angular velocity is sufficient or is significant or made man it follows that the that if the experiments made when the angular velocity is significant give a fringe variation on the photographic plate fixed to the mobile disk, we see we will see we will seek the cause of the influence of the speed of the disk compared to the laboratory in which it turns. And then so we got our experimental result. Second, 1 second, my lens popped out a little bit. All right. So let's see where are we at here. Experimental results. So here we got our fringe patterns and such displacements. We have carried out under the preceding conditions a series of tube recordings of an angle FCJ being equal to 120 degrees. So there's photograph 142 and 146, figure 9. The second series differs from the first only by a position of the vertical mirrors of the upper floor. So that's where you're seeing that slight separation there, but that's due to the how it has to, or how it's separating to go to the top of the fixed frame up above the rotating frame. The number of revolutions varied from 1.43 to 4 turns per second. The successive runs on the opposite direction of rotation were crossed such as to eliminate as much as possible the accidental variations of the fringe during the 5 minutes each run for the direction of rotation. The source of light remained as previously carbon arc. The plates were the same as the fringes above from the AGFA panchromatic sensitivity. So from the same type of light source used earlier, these fringe patterns were very similar, right? So photograph 146 of figure 9 represents the increased 4 times, or magnified 4 times. One of the recordings is carried out, the number of revolutions being approximately 3.6 turns a second. The fringes on the top and on the bottom of the test correspond respectively to the opposite directions of rotation of the mobile platform delta. The shifts of the two systems are not seen in photograph. I'm sorry. The shift of the two systems of fringes not seen in photographs 142 obtained when the speed of revolution is negligible is on the contrary very apparent for photograph 146 corresponding to a significant angular velocity. So measurements of the various photographs were made with the dividing machine provided. The following results express the distances between interference fringes of the mutual fringe shift delta of the two systems of fringes for the direction of rotation and the angular velocity of 1 turn per second for the mobile platform. The first series of experiments gave us delta with an average measurement of 15 recordings. The value for delta equals 0.058. The second series, made up of 7 recordings, provided a value of delta equals 0.054. In the final series, or in the first series, the individual values of delta were spread out between 0.052, the minimum value, and a maximum value of 0.017. Those are the second series value, not as good as the first, were between 0.046, the minimum value, and 0.078, the maximum value. So they were slightly off on the second ones. These experiments thus highlight the existence, under these conditions, of a shift of fringes of approximately 0.056, the distance between the interference fringes of white light for those two directions of rotations at angular speed of 1 turn per second. Although the precision of the operation does not allow us to exceed the approximation of a few percent on the median value, this phenomenon is beyond a doubt, and its cause must be sought in the influence of the number of revolutions of the platform on the propagation of light in the various using the various possible interpretations. And that is what we're going to consider now. So they give interpretations of the experimental result here. So we'll get into these. And then, let's see, we've been going for about an hour and 10. And we should have enough time to get into Robert Bennett's review of the experiment. Sorry, to give some more insights on it and its relevance here. So let us point out initially that the elements of the theory, let us point out initially the elements of the theories that we will apply here. The classical theory supposes, as one knows, for the observer fixed to the disk, that the speed of light in a point of a revolving disk differs from the speed of light of that in a laboratory, in a quantity of that plus or minus, equal or plus or minus that of the velocity. And if v represents the value of the absolute projection of the linear velocity of the disk at a point considered on the platform of the element of the considered on the platform, the element of the path is considered. So they're saying the length of the path, right? So the time that light has to travel, right, or whatever, right? The time of propagation, right? The rate of induction and all that, and the angular rotation of the device. Now, what we find out later in 2004 is that it's not just angular rotation that does this. You can derive this with linear motion as well. So we will use the relativistic theory we will use as the relativistic theory of these phenomenon that are given to us by Mr. Lavaux in 1921 and recalled by him more recently in citation number 3. In this form of interpretation, the observer is pulled by the moving disk and is supposed to adopt a central time coordinate t, which is that reported by the Galilean observer, in which the center 0 is chosen on the platform as motionless. So the center of the rotating disk is the location chosen for the relativist to do his math. So you're on your stationary, or you're in a position on the platform that can be considered stationary. So let us notice while passing that this selected center 0 is not necessarily the center, or not necessarily the center of rotation of the platform, but it is an unspecified point arbitrarily chosen on the disk. The form, which takes the fundamental invariant ds squared, implies an anisotropy in light propagation, of which the speed varies with the direction between c plus the omega, the angular rotation, times the radius of the device, and c minus the angular rotation and radius of the device, with the first order approximation in the rotation. In these expressions, omega is the angular velocity of rotation of the platform, and r is the distance from the center of 0 arbitrarily chosen at the point of passage on the disk of the light ray considered. Mr. Lavaux finds thus that the duration dt, your delta t, your change in time of the light course, uh, and the length, your DL, your change in the length is given for the direction of circulation for the or of light. Of light by the expression dt equals dl over c plus 2 times the angular rotation times dA over c squared, where dA is the area of a triangle, which is based on the dl top of the selected arbitrary center center 0, while integrating along the finished light course fixed to the revolving disk, and by taking account of the other direction of propagation, we can deduce the value of the displacement of the fringes Yeah, I don't know what word that means. Ascribable to the course considered. Ultimately, these two theories leads to as one knows, the following predictions respectively concerning the united finish trip on the return disk. The awaited shift of the fringes is, all things being equal, proportional to the area having for its base the path traverse time of light on the mobile platform, but on the top platform it is not the same for these two theories. In the classical, the top is the center of the rotation point C on the platform and is independent of the position point 0, where the traditional observer is supposed to be fixed. So instead of being at the center of the rotating device, they're at the center of the fixed portion. Let's see. It's supposed to be fixed. According to the relativistic theory, this top is arbitrary. We choose it just like on the beam splitter S at the point 0, where we are supposed to place the relativistic observer fixed in the mobile platform. We then have to apply these considerations when following the cases. 1. The optical circuit closed in its entirety, fixed to the revolving disk. This is the well-known case of the experiments of Sagnac. The two theories are here in agreement between them, and in agreement with the experiment with regard to the total shift of 8 fringes recording, of the 8 fringes recorded on the turning disk. However, the traditional theorist and the relativistic theorist are not in agreement between them on the distributions that they make of the cause of the phenomenon between the two various components of the total course, but so that the physicist operator who makes the experiment has the responsibility of choosing between these two theoretical interpretations, it would be necessary to take an experimental measurement directly of the speed of light on the platform in rotation, an operation which is obviously impossible to realize with the precision necessary in the current state of the art. So 2. Part of the optical circuit is fixed on the revolving disk, and the other part of the optical circuit remains fixed compared to the laboratory. Under these conditions, which are those of our experiments, the shift of the fringes is due obviously to the optical course fixed to the revolving disk. We will calculate these values, which return to us according to the two theories. So in the experiments made in accordance with the assemblies in Figure 6, the area included in the sector having for the base of the light train to FDEOKJ, and for the top of the path, center C of rotation of the platform, has the full algebraic value because the surface of the small basic triangle based on E and D in this figure must be counted as a negative. A prime equals 1,770 centimeters squared approximately, while the area of that on the same sector is based on the FDE0JK and those whose top item 0, where the observer is pulled by the disk and the algebraic has the full value of A equals 169 centimeters squared approximately. By introducing the numerical values into the expression, the fringe shift delta one finds with lambda equals 0.56 ohms. For the two directions of rotation, for the angular velocity of 1 turn per second, delta equals 16 minus A prime over E lambda equals 0.053 in fringes according to the classical theory. And in the relativistic theory, we have delta equals 16 minus A prime over E lambda, or over E times lambda equals 0.005 in the fringes according to the relativistic theory. That is to say that the value is approximately 10 times smaller according to the last theory than according to the theory preceding it. The relativistic theory thus seems to be in complete dissension with the classical theory and also with the result provided by this experiment. But given that, as the note of Mr. Lavaux appeared to allow the value to be reported higher, we consider that the center where the theoretical relativist must presumably place where the relativist must presumably be placed can arbitrarily be selected. The relativistic theory is found contrary to agreement with the classical theory in the experiment if the center is obligatory collinear to the center of rotation of the disk. The only point of the disk which can be a permanent origin for a Galilean axis not subjected to the rotation of the movement of the unit. So again, with the Galilean reference or whatever what they were talking about is a stationary point, stationary reference frame basically. So on a rotating device, the stationary reference point would be the center. And like I was saying earlier, shout out to my boy Riggs. What up, G? Like I was saying earlier, if they, in relativity theory, any point on that rotating disk should be able to derive the results. There should be no preferred frame. But if they're only able to derive the prediction from the center, then that's GG for then that's not true, right? So that falsifies relativity on its first and second postulate, right? So all reference frames not being equally valid and the speed of light changing. So let's see. So again, we have the classical theory derives the correct fringes, and the relativistic theory does not, unless you're at unless you choose that what's supposed to be an arbitrary position, but it turns out to be obligatory. So this is despite the explanation that Lavaux said to us, in which he has arrived at after being informed of the results of our experiments. GG. So after Paul Lavaux was told all this, he was like, nah, don't care. So note, Mr. Lavaux points out that observers related to an unspecified point 0 on the revolving disk can be regarded as motionless when they are first order experiments according to the angular velocity of rotation omega, and at this point, and it is this point of view which he has placed himself in his notes. Okay, so he's trying to say that because it's if you know the exact rotation of the device, of the disk, right, to the first order degree, you can just place yourself at the center of it, for like this is his like justification for it, right? So let's see. Yeah, I mean that's basically what he says, right? So that's it. All right, cool. So we're done on that one, and that was on a fringe movement registered on a platform in uniform motion, 1942, by Dufour and Prunier. And then we're going to look at, so now we're going to look at Robert Bennett here. I think this is an 8-page paper, so we'll knock this out real quick. And this is just a recap of everything that we just learned, right? So this is so the Dufour and Prunier is a new experiment. No one's really talked about it. So new concepts here. We're learning new stuff. So this is going to be this is an analytical review by Dr. Robert Bennett. So abstract. The 1913 Sagnac test proved to be a critical experiment that refuted relativity theory as Sagnac intended, and supported a model of an ether that could be entrained like material fluids. But it also generated more questions, such as what is the speed of light in the lab frame? And the lab frame being the stationary, non-rotating frame, right? What if the optical components of the interferometer were moving relative to others, some in the lab and some on a rotor frame, testing the emission model of light transmission? What if half the beam was directed on a plane of the rotor? All of these questions are answered here in an extension of the Sagnac tests that were done 29 years after Sagnac by Dufour and Prunier. So this is an analytical review of on a fringe movement register on a platform in uniform motion, 1942. So everything that we just read, this is all in regards to that. So a review. So this is some quotes that he laid out from the paper. A review. We used an optical circuit entirely fixed to a rotating platform, as did Sagnac. Under the same conditions, we found that the moving fringes observed are similar within 6%, whether the light source and photographic receiver be dragged in the rotation of the platform. As in the experiments of Sagnac, or they remain fixed to the laboratory. As in the experiments of Sagnac, or if they remain fixed in the laboratory. So Sagnac and Prunier found that the speed of light equals c plus or minus v in the rotor frame. So this is the rotating frame. Dufour and Prunier found that the speed of light equals c plus v. C plus. Man, I said that completely wrong. Sorry. Dufour and Prunier found that the speed of light equals c plus or minus v also in the lab frame, optical bench at rest, empty platform spinning below it. This alone disproves relativity theory as the speed of light is greater than the speed of light. Or I'm sorry, it can't be greater than or less than the speed of light. If it's going to be the speed of light, right? Sorry. Let's see. The second series of experiments described here was aimed to explore the fringe displacement due to the rotation in an entirely new condition where the optical circuit of the two superimposed interfering beams composed of the two parts of the series, one part which remains fixed in relation to the laboratory while the other is attached to the rotating platform. Moving fringes obtained under these new conditions were the same ones that allow for the classical Galilean theory. So this is the velocity addition, right? So the speed is going to be plus or minus the rotational velocity. The frame is determined by the location of the detector. So the parts of the optical system were in relative motion, yet the results were seen were the same. Right. All right. So the speed of light equals plus or minus the radius times the angular rotation equals c plus or minus v. This alone rejects the Ritz emission model since the last reflection before the detector would determine the speed of light, uh, but since it doesn't, the speed of light is always Galilean as above. So the final, yeah. So that guy had that theory that that the speed of light would be determined off of that last rotating mirror. I was kind of reading a little bit about that, and then so the Galilean uh, interpretation of it would be that any of the additional velocities that light incurs plus or minus due to the angular rotation or regular linear velocity, linear motion, uh, will add plus or minus to the speed of light, basically, right? So it's kind of what they're getting at there, or what he's getting at. So experiments in which the optical circuits is entirely supported on a rotating platform. One, preliminary experiments. We first we first of all have repeated the experience of Sagnac, in which all optical apparatuses is moving with the disk in uniform rotation. We used the same mirror as the Sagnac in his experiment, but yeah, so he's just reading over from the quote that we read earlier. So basically, they got their setup going on here, similar to Sagnac. In spite of some of the imperfections, they got results that were pretty much exactly the same as Sagnac. A recap of their second experiment: experiments made with the source light remaining fixed to the laboratory. So we have the source of light fixed to the lab wall, and it shoots into the rotating interferometer. The light beam travels through, hits its photographic plate. The first question we considered, blah blah blah. So the characteristics of this assembly, yada yada. So that was from the last one. So that is, so the speed of light is equal to c plus or minus v. It is seen that uh, to 5 or 6 per 1 precision, the average shift observed of the same value here is obtained with an ordinary Sagnac assembly, right? So let's see. 3, the experiments. So this is just recapping a little more. So experiments made by using a source of a photographic recorder remaining fixed to the laboratory. Okay, so this one is okay. Sorry, I had it confused from the last paper. So the third experiment was the source and the photographic recorder were both stationary, and the device was rotating. So the path of light, or light was traveling through the rotating device. One could ask whether the interferential phenomenon remains the same. Blah, blah, blah. Okay, so the average of the two values for the opposite rotation is 0.091 of the distance between the interference fringes differing only 3 to 4 over 100. The number obtained previously if the light source were fixed in the laboratory. All right, so the speed of light in this experiment equals c plus or minus v. It does remain the same with 3 or 4% the air. So when they're both stationary and the device is rotating, there doesn't seem to be any effect for this one. Experiments in which the optical circuit includes a series fixed part to the laboratory and part pulled in motion for the rotation. So let's see. That was where they had it set up where there was like a string attached to the recorder or whatever, and it would be dragged along with the device, so it would still be in motion, but it was independent of the uh, platform, right? So experiments in which the axle are fixed partly in the laboratory and partly pulled by the platform in rotation. Or no, that was just, I don't know. We'll keep reading. The preceding disadvantages resulted owing to the fact that the two interfering beams followed distinct paths. They disappeared when they were obliged, when we obliged the two beams to the following same course in opposite directions. Figure 6 gives in perspective of the diagram of the apparatus construction, which was useful to us. 8 mirrors G, H, G, I, and H will remain fixed in the laboratory. The source is not shown. It is fixed in the laboratory. Okay, so the stationary source was here. It shoots in, reflecting to the mirror. Beam gets all its reflections in, hits the wall, gets its recording, bounces back. Or no? Yeah. Okay, that's not the recording. It just hits the stationary mirror and then, okay, hits the stationary mirror, then comes back, hits JK, comes back through here, and then they get their reading at L prime, I think it was. Okay. Note that the two beams reflected to the 20 centimeters. Just want to make sure that this reconnects. All right, we should be good. Note that the two beams reflected to the 20 centimeters. Just want to make sure that this reconnects. All right, cool. We're back. Awesome. That is very convenient. So sorry about that. Internet disconnected. We're back now. Let's see. It looked like I was just wrapping up on this page, so we'll just start from the top here, and we'll finish this out, and we'll end on a high note here. So when the rotor is at rest in the lab frame, the speed of light equals c in both reference frames. When the rotor moves at v in the lab frame, the speed of light equals c plus or minus v in both reference frames. Special relativity is disproven. Emission theory is disproven. Ether entrainment, full dragging is supported. Galilean relativity is supported conditionally. Consider the lab frame results with the counterclockwise platform rotation and the counterclockwise half beam that produces the speed of light c equals plus v. If the other rotor drags the surrounding ether at its rotation, or ether at its speed v, then the Galilean addition of velocity, or the law of velocity, predicts that the speed of light will be c plus v as measured. This was Sagnac's insight. Sagnac's interpretation of the quotes, Sagnac's interpretation in quotes. This is from Sagnac, quote, "The interference of the light in a rotating interferometer of a special kind proves to depend on the rotation with respect to an inertial frame. Sagnac announced this result as proof of the existence of an ether, although there were still in 1913 many physicists who welcomed such a claim. The increasingly powerful adepts of relativity theory brushed it away. The Sagnac experiment soon became..." Sorry, that's not a quote from Sagnac. Sagnac didn't say this, my bad. Let's see. The Sagnac experiment soon became a textbook classic, and experts in relativity felt compelled to explain it in both the special and general sense. Numerous variants of the experiment have been performed from the interwar period to these days. Interest in the Sagnac effect grew enormously when laser technology turned it into an efficient gyroscopic device. The inertial frame for measuring rotation must be the ECEF, or the lab frame, as the ALFA theory proves. And this is Bennett's theory of the, I think it's, can't remember the acronym, but something flexible ether, or luminiferous flexible something ether. That's his interpretation of the effects being shown. where you got your rotating Earth, so your ECEF frame or lab frame, and then wait a minute, the inertial frame for measuring rotation must be the ECEF. So this is a non-inertial frame. This is a rotating frame, or it must be a stationary frame. Okay, I'm not quite sure I understand. Um, let's see. I showed that the interferometer using a closed optical path enclosing a given area and rotating plane on the path detects the movement of a system relative to the ether in space. So, relative motion of the ether in optical systems does not mean that the ether is fixed, but that the system could be fixed and that the ether is in motion. Oh, sorry, the fluid ether model. Sorry, that's not the acronym either. So, fluid. So, basically, what he's saying here is that the interpretation could be a stationary fixed Earth with an ether wind, right? The outcome of these measurements shows that the ambient space that in ambient space light propagates with a speed VO independent of the motion of the apparatus and the source of the optical system. This property of space describes the luminiferous ether experimentally. This is the experimental proof of a whirling relative ether wind that rotating system creates through its motion. Exactly. Oh, sorry. So the Sagnac test interpretation in quotes was, I think, Bennett's quotes, or like this is his interpretation of it. So a modern description would call this an ether vortex. In Fresnel's hypothesis of an ether, the half beams counterclockwise and clockwise to the rotation propagate in the ether with a speed VO independent of the motion of the interferometer. The phase of the counterclockwise beam gives accordance to the expression of C lambda VO, a lag acts in phase with the counterclockwise beam and advances the same amount of the phase of the clockwise beam propagating in the reverse direction. The Sagnac effect shows that the light beams are independent of the motion of the system components, but not of the ether motion. We may describe the luminous phenomenon without mentioning the ether, but that is not a satisfactory description. It does not give a satisfaction the satisfaction we feel by eliminating the direct action at a distance. Sagnac's interpretation makes physical local S ether on the platform motion interact no action at a distance. The observed interferential effect or interferential effect proves to be the optical whirling effect caused by the motion of the system with respect to the ether, and it directly manifests the existence of the ether necessary carrier of the luminiferous waves of Hudgens in Fresnel. In the new experiment, motion with respect to the ether had been a measured effect, and this effect was a first. Let's see. Let me start over. In the new experiment, motion with respect to the ether had a measurable effect, and this effect was of the first order in the applied velocities. So, by directly knowing the velocity, they could correspond the exact amount of fringe shift to be provided for the the motion relative to the ether, right? So, I mean, that's GG. Sagnac believed he had struck a fatal blow on relativity theory, proving the existence of the ether. The luminiferous ether proved by the effect of relative ether wind in a uniformly rotating interferometer. Sagnac never ceased to see his experiment as proof of a whirling ether. Your experiment will always remain a fundamental experiment, even one of the most fundamental experiments of physics. Yet it will not suffice to convince the staunch relativist of the existence of an ether for the relativists are men who purport to imagine waves that propagate in a medium whose existence they deny. Birkingensen's Birkinson's letter to Sagnac, and this is the great grandfather of Christopher Birkin. I don't want to butcher that. Jerkness. I don't know. Sorry, I'm butchering that guy's name. But this guy actually ended up writing uh, he has the most comprehensive research done on the plagiarism of Einstein and the fraudulence of the mathematics and who he plagiarized, when he plagiarized it, and all that, and like people that called him out on it, etc. And his involvement that his wife had in that. So very cool stuff. So the ALFA interpretation, the absolute lab frame in fluid ether. Finally, I knew we were going to get to that acronym. Okay, so the absolute lab frame in fluid ether. So consider the first lab frame results. The speed of light equals v with the rotor off, and with the rotor on, the speed of light is plus or minus v. Just as a headwind or a tailwind will add or subtract to a plane's speed, the light beams obey the Galilean laws of velocity addition. But why is the change in the speed of light, but why is the change in the light speed v the same as the rotor speed at the radius of the measurement? This exhibits a full ether dragging by the rotor's mass, producing v equals r times w in ether speed, sometimes called kinematic entrainment, since dynamics is not involved. The generalization of this phenomenon would require all motion of matter through the ether to drag at some speed, moving or co-moving for a co-moving drag. Now the rotor frame results, the speed of light equals v, the rotor off, the speed of light equals c plus v, rotor on. The same as the lab frame, but this raises the logical impasse, which is, if the ether is being dragged to the rotor, then it is always co-moving with the rotor when the ether frame of reference is at rest relative to the rotor frame. So the ether speed should be measured as v equals 0 in the rotor frame, and the ether and the rotor and the ether are co-moving, and yet the speed of light changes by v. In the lab frame, the ether was always measured in the frame, and ether drag correctly predicted the measurement of the speed of light. If the ether speed is always measured in the lab frame, then the speed of light would again be the speed of light equals c plus or minus v. Consistent with other tests, Sagnac 1932 and Wang fiber optic test in 2005 and Newton's bucket 1687, the explanation of Dufour and Prunier's rotor frame result is the absoluteness of the lab frame. All the predictions of motions and dynamics must use the lab frame as the inertial frame, since inertial frames are defined by those of which the laws of dynamics are valid. But there are not multiple inertial frames, since all reference frames are at rest relative to the lab frame are equivalent to it, such as the surface or interior volume of a geostationary satellite. The enigma of the Sagnac and Dufour and Prunier results is solved by making the Earth a universal frame for predicting the future motion using Newton's and Maxwell's laws. Yeah, so to end on the recap here, the all predictions of motions and dynamics must use the lab frame as the inertial frame. So all this like hypothetical, oh, you can use this frame, there's no preferred frame, yada yada. When things matter and they're actually trying to make predictive models of motion for things that matter, like for example, for orbital mechanics, the reason that they have to use a geocentric coordinate system for that is because the way that they're going to apply forces, like all the relevant forces and whatnot for these orbits, has to be done in a way that that represents reality, right? So when you're doing predictive modeling, you're doing it through dynamics, and through that system, you're starting off with a stationary point of reference, stationary, non-rotating. You're using that as your jumping off point. And what they were showing here is that the speed of light changes, um, even in the lab frame, right? So that's incompatible with relativity theory. Now, they don't touch on it in this paper really, but what Wang showed with the linearization of the Sagnac effect is that he showed that the linear motion also contributes to the interference pattern and not just the angular rotation. And in fact, the equation here, let me pull this up real quick. So the circular derivation for the Sagnac effect and the linear derivation here. So the only difference here is that this omega here represents angular rotation and this represents linear velocity, just regular straight movement, right? And the way that they were trying to previously explain the Sagnac effect was it was only due to this. And then Wang experimentally proved that this also contributes to it. And in fact, you can actually derive the circular effect using the linear effect. So, yeah, GG. So instead of changing it to the area, it's just the length of the device. Yeah, just derives it exactly the same. It's equivalent. So that's cool. All right, so that's some prerequisite information for what's hopefully coming up in the future. Here we got some exciting stuff coming up, and some reviews of these experiments and stuff coming out, and some new ones. So keep an eye out for that moving forward. Thanks for tuning in. You guys have a good night. See you on the next one.